Hi, Stu Schwartz from MasterMathMentor.com. This is video AB24. The topic is Indeterminate Forms and LHospitals Rule. It covers the AB manuals, pages 149 and 150. As we conclude the first half of this course, let's return to where our study of calculus began: limits. We first studied problems that were in the form of the limit as x approaches 2 of x minus 2 over x squared minus 4, or the limit as x approaches infinity of 1 minus 4x minus 5x squared over 3x squared minus x minus 4. In the first problem, we would plug in 2, and we would get 2 minus 2 over 4 minus 4, and we would get 0 over 0. In the second problem, we would ignore all terms except the highest power terms in both the numerator and denominator. Plugging in infinity, we would get negative infinity over infinity. Both of these, 0 over 0 and infinity over infinity, are called indeterminate forms. In both of these cases, there are rules that are followed that seem to give different results. In the first problem, we get 0 over 0. You've been told that a fraction with a numerator of 0 is 0. But you've also been told that a fraction with a denominator of 0 does not exist. So is the limit 0? Does it not exist? Or is it some other number? In the second problem, when we got negative infinity over infinity, you've been told that a fraction with a numerator that goes to infinity is infinity. However, you've also been told that a fraction with a denominator that goes into infinity is 0. So is the limit infinity or 0? Or maybe the infinities cancel and the answer is negative 1. Add to the conundrum, infinity is not a number and we can't treat it like a number. That is why these expressions are called indeterminate forms, as it is not clear what is happening in the limit. There are other indeterminate forms as well. However, these will not be studied in the AB course. They are handled in the BC course. But we take a look at them. 0 times either plus or minus infinity is indeterminate. The conflict is that 0 times any number is 0, but infinity times any number is infinity. Infinity minus infinity is indeterminate. You've always been told that any number minus itself is 0, but infinity is not a number. 1 to the infinity is indeterminate. You've been taught that 1 to any number is 1, but any number to the infinity is infinity. 0 to the 0 is indeterminate. You know that 0 to any power is 0, but any number to the 0 power is 1. And finally, infinity to the 0 is indeterminate. Infinity to any power is infinity, but any number to the 0 power is equal to 1. You learn techniques at the beginning of the year to solve these limit problems. In the first problem, the limit as x approaches 2 of x minus 2 over x squared minus 4, we factored the denominator into x plus 2 times x minus 2, and we were allowed to cancel the x minus 2's because since we were talking about the limit as x approaches 2, x was not equal to 2, and therefore the x minus 2's are not zeros, so you can cancel them. That gives us the limit as x approaches 2 of 1 over x plus 2, and that turned out to be 1/4. In the second problem, the limit as x approaches infinity of 1 minus 4x minus 5x squared over 3x squared minus x minus 4, the technical way to handle this is to divide every term by the highest power in both numerator and denominator, which is x squared. So we get the limit as x approaches infinity of 1 over x squared minus 4x over x squared minus 5x squared over x squared all over 3x squared over x squared minus x over x squared minus 4 over x squared. And this becomes the limit as x approaches infinity of 1 over x squared minus 4 over x minus 5 all over 3 minus 1 over x minus 4 over x squared. We use the fact that the limit as x approaches infinity of all of these fractions with x in the denominator is 0. So this becomes the limit as x approaches infinity of 0 minus 5 over 3 minus 0, and our answer is negative 5/3. However, these techniques will not always work. For instance, the limit as x approaches 0 of cosine x minus 1 over x squared minus x is 1 minus 1 over 0 minus 0, which is 0 over 0, which is indeterminate. However, there is no factorization we can do, so there's no cancellation that we can do. So how do we take this limit? In the second problem, the limit as x approaches infinity of e to the x plus x over x cubed. Again, we could divide out by the highest power term, but we have an e to the x over x cubed, and how do we handle that? That will still be infinity over infinity. So this technique will not work. L'Hospital's rule, which was named after the 17th century French mathematician Guillaume de L'Hospital, allows us to evaluate limits involving indeterminate forms. An alternate spelling is L'Hospital with a circumflex O. L'Hospital's rule is amazing in its simplicity. It says that if a is a real number, infinity or negative infinity, then if the limit as x approaches a of f of x over g of x is equal to 0 over 0, or the limit as x approaches a of f of x over g of x is equal to plus or minus infinity over plus or minus infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. We call 0 over 0 and infinity over infinity indeterminate forms. Students sometimes confuse L'Hospital's rule with the quotient rule. They are completely different. The quotient rule is taking the derivative of f of x over g of x, while L'Hospital's rule is concerned with taking the limit as x approaches a of f of x over g of x. And that means that we take the derivative of the numerator over the derivative of the denominator. In the following problems, you are to use L'Hospital's rule to find the limit. In number 1, we have the limit as x approaches 2 of 3x squared minus 7x plus 2 all over x minus 2. Our first step always is to plug in, and we get 0 over 0. That's indeterminate, so we apply L'Hospital's rule and get the limit as x approaches 2 of 6x minus 7 over 1. Plugging in, our answer is 5. Here is graphic confirmation. The expression simply graphs a line, but there is a hole at the point 2, 5. However, as x approaches 2, the expression approaches 5. 2 involves some algebra. The limit as x approaches negative 3 of x plus 3 all over the square root of x squared minus 5 minus 2. Plugging in, we get 0 on top, and on the bottom we get the square root of 4 minus 2, which is 2 minus 2, which is 0. So L'Hospital's rule can be used. The derivative of the numerator is 1. The derivative of the denominator is 1/2 x squared minus 5 to the negative 1/2 times 2x. We can bring the square root to upstairs and get the limit as x approaches negative 3 of the square root of x squared minus 5 all over x. Plugging in negative 3, we get negative 2/3. Again, graphic confirmation. This function is defined when x is greater than the square root of 5 or x is less than negative square root of 5, and we only show the section that includes x is equal to negative 3. There is a hole on the graph at the point negative 3, negative 2/3. L'Hopital's rule can be used repeatedly in problems. 3 and 4 illustrate that. Number 3 reads, the limit as x approaches negative 2 of x cubed plus x squared minus 8x minus 12 over x cubed plus 8x squared plus 20x plus 16. Plug in negative 2 and you get 0 over 0. So applying L'Hopital's rule, we get the limit as x approaches negative 2 of 3x squared plus 2x minus 8 over 3x squared plus 16x plus 20. Plug in negative 2 again, and again we get 0 over 0. So we apply L'Hopital's rule one more time. The limit as x approaches negative 2 of 6x plus 2 over 6x plus 16. Now we get negative 10 over 4, or negative 5/2. Here is graphic confirmation with the hole at the point negative 2, negative 5/2. Notice, though, that if we had asked for the limit of this expression as x approaches negative 4, we would end up with a does not exist. That is because the denominator has a limit of 0, but the numerator does not. So this graph has a vertical asymptote at x is equal to negative 4, but a hole at x is equal to negative 2. Number 4 reads, the limit as x approaches 1 of x cubed minus 2x squared plus x over x cubed minus 3x squared plus 3x minus 1. Plug in 1 and we get 0 over 0. So applying L'Hopital, we get the limit as x approaches 1 of 3x squared minus 4x plus 1 over 3x squared minus 6x plus 3. Again, we get 0 over 0. So we apply L'Hopital one more time, and the limit as x approaches 1 of 6x minus 4 over 6x minus 6. We get 2 over 0, which means that the limit is undefined or infinite. Our graphic confirmation shows that indeed this graph has a vertical asymptote at x is equal to 1, and therefore the limit as x approaches 1 of this expression does not exist. Repeated use of L'Hopital's rule also works very well with trig functions and exponentials as well as natural logs. In number 5, we're interested in the limit as x approaches 0 of cosine x minus 1 over x squared minus x. Plugging in 0, we get 1 minus 1 over 0 minus 0, or 0 over 0. So applying L'Hopital's rule, we get the limit as x approaches 0 of negative sine of x over 2x minus 1, getting 0 over negative 1, or 0. The graph confirms the hole at the origin. However, the graph also illustrates a danger with L'Hopital's rule. If the problem had asked the limit as x approaches 1 of the expression, the denominator would be 0. However, the numerator would be the cosine of 1 minus 1, which is not 0. However, if you applied L'Hopital's rule, you would get that the answer would be negative sine of 1. And that is clearly not true, as there is a vertical asymptote at x is equal to 1. The moral of the story is that unless you get a 0 over 0 or infinity over infinity when you plug in, you may not use L'Hopital's rule. Number 6 reads, the limit as x approaches 1 of natural log of x minus x plus 1 over e to the x minus ex. Plugging in 1, we get 0 minus 1 plus 1 over e minus e, and that's 0 over 0. We then use LHospitals Rule and get the limit as x approaches 1 of 1 over x minus 1 over e to the x minus e, which is 1 minus 1 over e minus e, which again is 0 over 0. Rather than get rid of the complex fraction, we will just apply LHospitals Rule one more time to get the limit as x approaches 1 of negative 1 over x squared over e to the x. And plugging in 1, we get negative 1 over e. The graph confirms the whole at the point 1, negative 1 over e. Number 7 reads, the limit as x approaches 0 of 2 sine x minus sine 2x over sine x minus x cosine x. We first plug in 0 and get a 0 upstairs and a 0 downstairs, and we get the indeterminate form 0 over 0. So carefully applying LHospitals Rule, we get the limit as x approaches 0 of 2 cosine x minus 2 cosine of 2x over cosine x plus x sine x minus cosine x. Plug in and we get 2 minus 2 over 1 plus 0 minus 1, or 0 over 0. So we apply it again, and we get upstairs negative 2 sine x plus 4 sine 2x over x cosine x plus sine x. When we plug in 0, we get 0 plus 0 over 0 plus 0, or 0 over 0. So, one more time, the limit as x approaches 0 of negative 2 cosine x plus 8 cosine 2x all over negative x sine x plus cosine x plus cosine x. And plugging in 0, we get negative 2 plus 8 over 0 plus 1 plus 1, which is 6 over 2, or 3. The graph shows the confirmation with the hole at the point 0, 3. Actually, this graph has an infinite number of holes, but only one where the x value is an easy point, like x equals 0. L'Hopital's rule can also be used with limits as x approaches infinity. Number 8 reads, the limit as x approaches infinity of 1 minus 4x minus 5x squared over 3x squared minus x minus 4. Plugging in infinity, we get negative infinity over infinity. So we apply L'Hopital's rule, taking the derivative of top and bottom, getting negative 4x minus 10x over 6x minus 1. Plugging in infinity, we still get negative infinity over infinity. We then apply L'Hopital's rule one more time, and we get the limit as x approaches infinity of negative 10/6, which is negative 5/3. Of course, a far easier way to do this is to look at the highest power terms and their coefficients. Since the highest power is x squared in both top and bottom, the limit is negative 5 over 3. Asking the limit of a function as x approaches plus or minus infinity is really asking whether the graph has a horizontal asymptote. Graphical confirmation shows that it does at y is equal to negative 5/3. And whether we ask for the limit as x approaches infinity or x approaches negative infinity, in this case it does not matter. The horizontal asymptote is at y equals negative 5/3. However, that method will not work in number 9, the limit as x approaches infinity of 4x squared minus 5x plus 2 over e to the 5x plus natural log of x, because our denominator is not a polynomial. So we plug in infinity and we get infinity over infinity. And we now use LHospitals Rule to get the limit as x approaches infinity of 8x minus 5 over 5e to the 5x plus 1 over x. Plugging in infinity again, we still get infinity over infinity. We then use LHospitals Rule one more time, and we get upstairs an 8, and on the bottom 25 e to the 5x minus 1 over x squared. And the limit as x approaches infinity of that expression is 8 over infinity, which is 0. The graphical confirmation shows that this curve has a horizontal asymptote along the x-axis. And it also illustrates what is really happening with L'Hopital's rule. Both the numerator and denominator, as x gets larger and larger, are getting larger and larger, but the denominator gets larger at a much, much faster rate than the numerator. That's why, in this case, infinity over infinity has a limit of 0. Congratulations! You have completed differential calculus and you are over halfway through this course. The second part of the course is integral calculus. And while concerning itself with a basic problem much different than the slope of the tangent line to a curve, with different notation and procedures, it builds on differential calculus, and when combined, allows us to explore many practical solutions that occur every day in the area of physics, economics, medicine, astronomy, acoustics, electricity, biology, engineering, and epidemiology. So stay tuned.